Good morning, dear students. My name is Ferhan Mazher, and today is 19th April 2022. Right now, I am with the 11th Cambridge class, and the subject we are studying is Physics 5054. This is Cambridge O Levels Physics, and the code of this physics is 5054. Today, we have selected a theory paper, and today we will solve the section B of this paper. Today's paper is May-June 2012 2-2 paper. This paper belongs from the Zone 2, or you can say Variant 2. The section A of this paper I have already solved, and you can find that video in the same playlist of my channel. Today in this session, we are going to attempt the section B. The section B comprises of 3 questions, question number 8, 9, and 10. We will attempt all these questions. So hope you will enjoy this session and you will learn from this session. So let's start today's paper. So here we go. It says section B, May, June 2012, 2-2 paper. A student investigates how the resistance of a wire depends upon its length. The student uses an ammeter, a voltmeter, a battery, a fixed resistor, and the wire under test, all connected in an electric circuit. In the space below, draw a circuit diagram of the apparatus. Label the wire under test with the letter W. So it's a 3 marks question. Let me reduce the size. You can see the whole question. So here we go. Question number 8. So here you can see I have drawn this diagram, the circuit diagram. I have shown a battery, an ammeter, a fixed resistor, and then we have taken a wire. I have used the crocodile clips, and the left crocodile clip is on the start of that wire, and the other crocodile clip, which is on the right side, that can be moved. It can be put anywhere on the wire. So the wire which will be between the crocodile clips, that will be in use, that will be included in the circuit. I have also placed a rule there, so I can check what is the length of the wire being used. So then we have put a voltmeter. The voltmeter is parallel to the wire. So it will tell you the voltage drop across this wire, the length of the wire which is being used, and the ammeter will tell you how much is the current flowing through that wire. So this is the circuit diagram which you have to draw. So hopefully you understand. So let's go to the, he says containing in any circuit a battery, cell, power supply, ammeter, voltmeter, and fixed resistor. Ammeter clearly measures current. Okay, so that's the next question through the W, and the voltmeter clearly across the W if W is shown, or a resistor if not. So this wire is W. So we have to label this thing. Okay, so I have not labeled it. So let me label this thing also. So with the red ballpoint, we have to label the wire. We have to label the wire with the letter W. So here you have to write W. So that's very important. Okay. So keep. So we have to label it also. Okay. So now we are going to the next part. He says describe how the student obtains one complete set of results. So what the student will do, he will switch on this circuit. You can put a switch here. So when you close the switch, immediately he will note down what is the reading on the ammeter. He will note down what is the reading on the voltmeter. He will note down how much is the length of the wire being used. And then you can tell the resistance. The resistance will be the voltage divided by the current. So let me show you my answer. Set apparatus as shown in the above figure. Note ammeter and voltmeter reading. Calculate R equals to V by I. And they change the length of the wire by moving the crocodile clips away from each other. and repeat the procedure. So you will find that the different lengths have different resistance. Okay, so where we go. Resistance calculated V by I or R, V is equals to I by R seen, length of the wire, all three measured, change length and V and I measured. So this is how you will answer this question. So we have written the same thing. Okay. The third part, during the experiment, the student keeps the temperature of the wire constant. So that's why it's sensible to keep the temperature of the wire constant. You see, if the temperature of the wire will change, its resistance will change. So it's very important to keep the temperature of the wire constant. Then the question is suggest how the student keeps the temperature of the wire constant. You can keep the temperature of the wire constant, but you will switch on the circuit. Immediately you will note down what is the reading on the ammeter, what is the reading on the voltmeter, and then you will switch off the circuit. So the wire will not get hot, because when current flows through the wire, due to the resistance of the wire becomes hot. And when the wire will become hot, its temperature will change and its resistance will also change. So let me show you my answer. Then we will check the answer from the marking scheme. Here we go. If the temperature will change, resistance of the wire will change. And switch on the circuit and note the readings and switch off the circuit immediately. Okay, so that's our answer. So let's have a look at the marking scheme. Resistance, resistivity changes with the temperature, or wire gets hot and melts, burns, catches fire, dangerous, or V only proportional to I at constant temperature. Use of water bath, heat sink, use small currents, take readings quickly and switch off. We have given this answer. Okay, so next question. The figure 8.1 shows part of a circuit containing three resistors X, Y, and Z. The resistors of X and the resistors of the Y are each 10 ohm, and the current through the X is 0.30 ampere. The current through the Y is 0.2 ampere. Calculate the potential difference across the Y. So we have to find the potential difference across the Y. I know the current flowing through the Y. I know the resistance of the Y. So very easily we can find the voltage drop across the Y. V equals to IR. So you can use this formula. It's a 2 marks numerical. Let me show you my answer. So here we go. So we know that V is equals to IR. So I is 0.20, multiply resistance is 10 ohm. So it will be 2 volt. So the voltage drop across the Y will be 2 volt. Okay. So let's check the marking scheme. It says 2 volts. So our answer is right. Okay. The next part. Calculate the current I in the resistor Z. So you can see from the main, the current coming is 0.3 ampere. So here there are two branches. So the current was divided. In the upper branch, the current is 0.2 ampere. So in the lower branch, how much will be the current? That will be 0.3 minus 0.2. So let me show you. So it will be 0.3 minus 0.2, and that will be 0.1 ampere. Okay. Now, 0.1 ampere. Then the question is, explain in words rather than by calculation how the figure 8.1 shows that the resistance of the Z is larger than the resistance of the Y. Use ideas about the potential difference and the current in your answer. You see, because Z and the Y, they both are parallel to each other. Let me show you. This Z and the Y, they both are parallel to each other, and the voltage drop across the Y is 2 volt. Because Z and Y, they are parallel to each other, so both these branches will have the same voltage drop. So it means the voltage drop will be same in the Y and the voltage drop will be same in the Z. Because the current flowing through the Y is 0.2 ampere, which is 2 times the current flowing through the Z, which is 0.1 ampere. You see, the voltage is equals to V is equals to IR. So because V is constant in both this, so V is equals to IR. If somewhere the current will is doubled And in the other branch, the current is half. In one branch, the current is 0.2 ampere. In the other branch, the current is 0.1 ampere. So the current is half in the lower branch through the Z. You see, if the current will be half, the resistance has to be double to get the same value of the voltage drop, because V is equals to IR. If the I value will become half, the R value has to be doubled to get the same V value, because V is equals to IR. If the voltage is supposed to remain same, then if the current will become half, for example, in one branch it is 0.2 ampere, in the other branch it is 0.1 ampere, then the resistance in that Z branch has to be doubled to get the same voltage. V is equals to IR. So it's a 2 marks question. It's a star question. Note it down. Okay, so let me show you my answer. R is equals to V by I. Voltage drop in Y and Z is same because I in the Z is smaller. So V by I ratio for Z will be larger. So it means that the R value will be greater. I hope you understand this question. It's a 2 marks question. So let's have a look at the marking scheme, what the marking scheme has to say. Okay, Z has the same potential, different voltage. Z has less small current, thus larger resistance. Okay, that was our answer. So by 2 methods, I have explained you. Okay, calculate the total resistance of the resistor X, Y, and Z in this circuit. So the resistance of the Z is 2 times the resistance of the Y. So if this is 10 ohm, this will be 20 ohm. So their combined resistance I can calculate, and then once I know the combined resistance of the Y and Z, then I will add this combined resistance with the resistance of the X. So that will give me the total resistance of this whole circuit. So let me show you my solution. So the RZ will be V by I 2 volt divided by 0.120 ohm. So the combined resistance of the Y and Z will be 1 by R equals to 1 by R1 plus 1 by R2. So 1 by R is equals to 1 by 10 plus 1 by 20. So 1 by R will be equals to 2 plus 1 by 20, and 1 by R will be equals to 3 by 20. So 3R will be equals to 20, and R will be 20 divided by 3. So now I know the combined resistance of Y and Z. So whatever is their combined resistance, I will add that resistance into the resistance of the X, and that will give me the total resistance of the whole circuit. So Rx plus RYZ will be 10 ohm plus 220 by 3 ohm. So take the LCM 3, and so it will be 30 plus 20. So it will be 50 divided by 3, and that will be 16.67 ohm. So the total resistance of the whole circuit will be 16.67 ohm. So let me check the marking scheme. So 16. Yeah, this will be the answer. Yeah, our answers are right. So my dear students, we are done with the question number 8. Hopefully you understand this question. So we are done. Yeah. Question number 9 is showing up on your screen. So question number 9, it says figure 9.1 shows 2 coils of insulated wire wound on an iron ring. Coil A is connected to a battery and a switch. The switch is open. Coil B is connected to a sensitive center 0 voltmeter. So here you can see we have a soft iron ring. And on this ring, here we have a coil A. We call it primary coil. And it has 1, 2, 3, and 4 turns. And it is connected with a circuit, a battery, a switch. Switch is open right now. This is coil B. We normally call it the secondary coil. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Approximately 16, 17 turns there. And this is called the secondary coil. Coil B is its name. And we have a voltmeter connected with this coil. So the switch is closed. There is a current in the coil A. So what's the question? On the figure 9.1, mark the direction of the current in the coil and draw the magnetic field lines produced in the iron ring. You see, this is your coil. Coil A is connected with the battery, and here we have that coil. And let me show you. Let me switch on my camera. So I'll switch on camera. Let's change the direction of the camera. Okay, so now you can see this camera. So here we go. So here we have that camera. So you can see, and when I will close this switch, so when I will close this switch, the current will come from the positive. We are talking about the conventional current. So the current will come from here. From here, the current will go in this direction. Current will go in this direction. The current will go in this direction. Current will go in this direction, and it will go back to the battery. So we are talking about the conventional current. So I will use the right-hand grip rule for the solenoid, and I will hold the solenoid in my right hand. This is my right hand. Okay, so this is my right hand. So I will hold this solenoid in such a way that, you see, I will hold it like this. The curls of my fingers are along the direction of the conventional current, and my thumb will point in the direction of the, north of that electromagnet which will be formed on the coil A. So when the current will flow through the coil A, you see the coil A will become an electromagnet and its north will be in the downward direction. How do I know this? I'm using the right hand rule. The curls of my finger, they are along the direction of the conventional current in that solenoid, and my thumb is pointing towards the north of that electromagnet. So the north pole will be here and the south pole will be here. So from here, from the north, the magnetic lines will go and they will go to the south pole. So in this iron ring, the magnetic lines will start from here, which will be the north pole of that electromagnet, which is in the coil A, and they will go to the south pole here. So they will be going like this. So I can draw this. So let's switch off the camera. Okay. So now the question is, mark the direction of the current in the coil A. Okay, we will do that. And draw the magnetic field lines produced in the iron ring. It's a 3-mark question and a 1-mark question. So let me show you. So here we have, so you can see the current is conventional current. So the current will come from here, and this is the direction of the current in the coil, and here the current is going back. So here the solenoid, this will be the north pole and this will be the south pole of the that coil A when it become electromagnet. So from here the magnetic lines will come out and through the iron ring they will travel, and here in the south pole they will go back. So this is how you will draw this. It's a 4-mark total question, and I hope you have understood. So let me show you the markings. Conventional current direction correct in the coil 1 lead, at least 1 line axially through coil A, or line above and below end of the coil A, at least 2 curved lines in the ring from ends of A to ends of B, and inside the A and B, correct direction on at least 1 line arrow of the candidates. That's right. So it's a 4-mark question. So we are done with this. I hope you have understood. Then the B part, he says, as the switch is closed, the voltmeter deflects to the right and then returns to 0. So what they are saying, explain why there is a deflection in the voltmeter. So when you closed it, this voltmeter deflected to the right and then came back to 0. So why this happened? So their question is, explain why there is a deflection in the voltmeter. So you see, when you close the switch, the coil A became an electromagnet. Its magnetic flux started flowing through the iron ring through the coil B. So the magnetic flux passing through the coil B has changed. Due to that changing magnetic flux, the EMF is induced in the coil B, and due to that induced EMF, the voltmeter has shown a deflection to the right. And you see, when you keep the switch on, the magnetic flux flowing through the coil B will become constant. When the magnetic flux flowing through the coil B will become constant, there will be no change in the magnetic flux passing through the coil B. There will be no EMF induced in the coil B. So the voltmeter will show zero reading. So I hope you understand what I'm saying. And let me show you the written answer. So magnetic lines passing through the coil B were zero. Then there were magnetic lines passing through the coil B. So EMF, it means that the magnetic flux passing through the coil B has changed. So before, when the switch was open, there was no magnetic lines passing through the coil B, and now they are passing through the coil B. So EMF was induced due to changing magnetic flux. Thus, flux becomes constant, and due to the change, then the flux becomes constant, and EMF induced in the coil B will become zero. That's why the ammeter, the voltmeter, will show the zero reading. So I hope you understand. Okay, let me show you the marking scheme. Voltmeter deflects to the, he says magnetic flux field cuts the coil B, or field or flux changes in the coil B, induces an EMF and voltage current in the B. Okay, so then the next part is, without changing coil A state, he says then the switch is open. State and explain what happens to the deflection on the voltmeter. The deflection, when you close the switch, the deflection in the voltmeter was towards the right. When you will open the switch, the deflection will be produced again in the voltmeter, but this time the direction of that deflection will be towards the left, and then it will become zero. So why this will happen? Because because when the switch is closed, the magnetic flux is passing through the coil B, which was produced by the electromagnet of the coil A. So when you switch off the current, the coil A will be no more electromagnet, and so there will be no more magnetic flux passing through the coil B. So now the magnetic flux has changed, and there was magnetic flux, and now there is no magnetic flux passing through the coil B. So the magnetic flux passing through the coil B has gradually decreased. So that's why the EMF induced has opposite direction to which it was produced in the previous part. So now the deflection of the voltmeter will be towards the left instead of towards the right, which was in the first part. So I hope you have understood this, what I'm saying. So let me show you my written answer, and here we go. The magnetic flux passing through the coil B changes and becomes zero. So EMF is induced, but its direction is opposite to the B first part. Deflection will be opposite. Deflection will be to the left side. So next, then their question is, without changing the coil A, state 2 changes to the apparatus that causes a greater deflection of the voltmeter. So increase the number of the turns of the coil B. Coil B is the secondary coil. If the number of turns of the coil B will become larger, a larger voltage will be induced in the coil B. And the second thing, you can increase the cells of the battery. If you increase the current in the coil A will become a stronger magnet, and that's why the EMF induced in the coil B will be also larger. So let me check what are the answers. So you can see, it says the second part, B second part, it says voltmeter deflects to the left opposite and returns to zero. Flux field decreases, collapses, reduces, or iron loses magnetism, or change in the field is in the opposite direction, or to oppose the flux or field change. Then he says any two lines, more turns on the coil B, larger voltage current, for example, of the battery, more cells, battery smaller, the internal resistance of the battery should be smaller, smaller resistance of the wires, thicker wires, shorter wires, thicker or shorter iron ring, use soft iron, coil A and B closer on the ring, or more sensitive voltmeter, or laminate the iron ring. Okay, so that is the answers which they have given. You can choose anyone. Okay, so now we are going to the C part. He says the battery in the figure 9.1 is replaced by an alternating supply. The output from the coil B is used to power a lamp that is a long distance away. From the lead from the coil B to the lamp has a resistance of 2.5 ohm. So the wire which is coming from the supply to the lamp, its resistance is 2.5 ohm. These leads are represented by the two resistors shown in the figure 9.2. The output voltage of the coil B is 240 volt and the current in the circuit is 1.6 ampere. Their question is calculate the electric power produced by the coil B. You know the electric power is equals to IV, and I know the current which is 1.6 ampere. I know the voltage which is 240 volt. P is equals to IV, and very easily we can find out the power. So the power will be equals to IV. So the power will be equals to 1.6 multiplied 240, and that will be 384 watt. 384 watt. The data is in two significant figures. Our answer is in three significant figures, so we can reduce it. So let me see. You see, it has written 380 watts. 384 is also right. Then the question is calculate the total power loss in the leads to the lamp. Leads to the lamp. Okay. So the total power, the power loss here plus the power loss here. So very easily we can find the total power loss, and let me show you. The total power loss, you know, the power loss formula is P equals to I square R. We know the current flowing through this wire, that is 1.6 ampere, and we know the total resistance of the leads, that is 2.5 plus 2.5, and that will be 5. So 5 multiply 1.6 square, that will be 12.8 watt, and this is in three significant figures, but our data is in two significant figures. So I will reduce my answer to two significant. I will round it off to two significant figures, and so the power will be 13 watt. 12.8 watt. It will be 13 watt approximately. So let's check the marking scheme. What the marking scheme has to say. 12.8 watts or 13 watts. So we are done. We are done with the question number 9. Okay. Here we go. Question number 10 is on your screen. To find out whether a radioactive source emits alpha particles, beta particles, or gamma rays, the source is placed in front of a radiation detector as shown in the figure 10.1. Different absorbing materials are placed between the source and the detector. The detector measures the number of counts per minute. Okay, state what is meant by an alpha particle. An alpha particle is like the nucleus of helium. It has 2 protons and it has 2 neutrons. It has positive 2 charge on it. So let me show you my answer. Alpha particle has 2 protons and 2 neutrons. It is like the nucleus of helium. It has positive charge. Its charge is positive 2. Then the question is, let's have a look at the question paper. Then the question is, state what is meant by the gamma rays. Gamma rays are electromagnetic waves, and they have very high frequency and very short wavelength. Let me show you. Gamma rays are electromagnetic waves. It has high frequency, high energy, small wavelength. So this is our answer. So let's have a look at the marking scheme. So he says 2 protons has charge positive 2, like helium nucleus. Okay. So then he says 2 neutrons has mass 4, and the symbol of the alpha particles He24. Okay. Electromagnetic particles or waves, high frequency, high energy, low wavelength. That is our answer. So our answers are right. So just why this experiment, the distance between the source and the detector is only a few centimeters. You see, the distance between the source and the detector is only a few centimeters because it's emitting alpha particles. If it's emitting alpha particles, then the penetration power of the alpha particles in the air is just few centimeters. So even if the source is producing alpha particles, but your detector is, let's say, a few centimeters away from the source, the alpha particles will not be able to reach the detector. The reason is that the penetration power in the air is just few centimeters. They collide with the air molecules and they are stopped. So the distance between the source and the detector should be small, so that if the alpha particles are being produced, they can reach the detector and it can detect it. My written answer is this is because alpha particles have penetration of 4 to 5 centimeter in air. Then the question is, the half-life of the radioactive source is longer than a few minutes. The half-life should be longer than a few minutes, so that you can perform your experiment, so that you get enough time when you are working with that radioactive sample, that before it completely decayed, you can complete your experiment, your observations, your readings. So sample can last during the experiment. So at least during the experiment, it should not go vanished. All the samples should not go decayed. Okay, so the alpha identified as the reason the alpha particles stopped, blocked, absorbed by the few centimeter of the air, or distance covered by range of alpha particles in the air is small, a few centimeters only. Experiment takes time in some way, or otherwise count falls during the half-life. Okay, so because when you are taking the readings and the reading might reduce due to the half-life. If, for example, half-life has passed during your experiment, the reading will go down because of the half-life has been completed. Okay. He says, state one precaution taken when using a radioactive source. Whenever you use a radioactive source, always work from a distance keep your distance from the radioactive source. Always use forceps and tongues to handle the radioactive source, and always wear the lead lining suits. Okay, so we have only to write here only one precaution. Okay, yes, it can. Where is our answer? Precautions. I think I missed that answer. Okay. So let me show you. I think I have not. I forgot to include that. So you know what are the precautions. So let me show you from the marking scheme. Keep distance. For example, use forceps tongues. Do not point at person's eye. Use absorber. For example, lead covering. Place in store. Place in store when not in use. Use for short time. Wear badges. Your exposure time to the radioactive sample should be kept minimum. Okay. Then the question is, figure 10.2 shows the results obtained. Okay. So when there is no source, no material between the detector and around the detector, so the count rates are 10. So that is the background radiation. So without source, the reading in the environment is 10 counts per minute. Then they put the sample in front of the detector. Nothing is between the detector and the source, and the reading you get is 1200. Then you put a thin paper between the detector and the source, and the reading drops from 1200 to 820. This shows that there was alpha particles, because the alpha particles are stopped by the paper. So when you put paper between the detector and the source, and the reading dropped on the count rate, the reading dropped from 1200 to 820, that shows that the alpha particles are present in that radiation, because alpha particles can be stopped by the paper. Then he says, then he put a aluminum, 5 millimeter thick aluminum foil. The reading has changed from 1200 to 820. You can see that when you put the papers, you get the same reading. When you put the aluminum foil, you get the same reading. It means that there are no such rays which can be stopped by the aluminum. So it means the beta particles are not there because the beta particles cannot pass through the aluminum. Gamma rays can pass through the hair. So it means that the source is emitting the alpha, the source is emitting alpha particles and it is emitting gamma rays, because the gamma rays cannot be stopped with the 5 millimeter thick aluminum foil. So these are the three answers. Okay. Yes, it emits alpha particles. Count rate dropped from 1200 to 820 when paper was between detector and the source, and the alpha particles cannot pass through the paper. Beta particles are not emitted. Count rate in presence of the paper is 820. In the presence of aluminum is still 820, which means that the beta particles are not given out. Gamma rays, the gamma rays are present because in presence of aluminum between the detector and the source, reading has not dropped to 820. Okay, let's check the marking scheme. The question is, yes, alpha particles present and count falls with paper in some way. No beta particles when 5 millimeter aluminum was used, and no further or more extra reduction or no difference. Yes, gamma present and the gamma passed through the 5 millimeter aluminum or 820 after aluminum. Okay. So that was the C part of the question number 10. I think question number 10 or question number 11. It is question number 10. Yes, we are doing it. Then he says there is a count recorded even when no source is present. This is caused by the background radiation. State two sources of the background radiation. There can be many sources of the background causes of the background radiation. Some of them are the cosmic rays. From the outer space, the radiation is coming into the earth. We call it cosmic rays. And then we have there is some minerals in the soil which also are radioactive. You have to write two reasons. So there might be some nuclear waste dumped in your area. That can also be a reason. Cosmic rays and the minerals in the soil. Then the question is, describe one effect on the human body of a very high level of radiation. You see, the high level of the radiation can damage the DNA, thus it can cause birth defects in the newborn babies. So let's have a look at the marking scheme. It can cause cancer, tumors, radiation sickness, burns, mutation, genetic problems, damage to the DNA or the chromosomes. Cell damage, for example, kills cells, cures cancer, birth defects, sterility, hair loss. Okay, so my dear students, so we are done with this paper, and today we have done May-June 2012 Physics 505422 paper. Today in this video, in this session, we have done the section B of this paper. The section A of this paper we have already done, and you can find the link of that video just above this video in the playlist. I hope that you have learned something from this video. I hope that by sitting in your home, by just looking on your smartphone or your LEDs, you are able to practice the physics past paper at your home. And that is the purpose of these videos. That by sitting in your home, you can do these past paper practices and you can have an expert's opinion on answers. So it's a great blessing for me to teach you all. So thank you very much, everyone. who are watching these videos. If you like this video, please share the link of this video onto your Facebook, onto your Instagram, and onto your Twitter accounts. And also like my video. Also subscribe my channel, because that is like fuel for me. So thank you very much. It's a great pleasure for me to be helpful to you. Thank you very much. Have a good day. God bless you all.